Hey, how y'all doing? Like one thumbs up. Okay, we'll take it. So we're going to start up in about 2 minutes with a couple announcements, sort of a recap of where we've been, where we're going in the very near term, and then sort of dive in on one more announcement, and then a little bit of discussion about the theory in the current section that we're diving in on, and then we're going to be working on a lab today. And if you haven't yet checked your email, the lab contents should be there along with the example that I'm working through in class. In addition to that, all those files are found in the Lab 5 section of the Canvas. Okay. So I'm going to start by maybe grabbing, let's just start with a description of a couple announcements. 12:09, I guess I shouldn't start until 12:10 with the announcements. Anyone got something to do for 30 seconds or so? Okay, still waiting one more minute by my clock before we start up. Some of you are wondering, why is there a bookcase behind me? Well, it's virtual, but it's mine at least. Have you ever wondered about those people on TV that have the, really cool looking bookcases and then wonder why 3 or 4 of them have the exact same bookcase behind them on TV? Yeah, that's awkward. It's like wearing the same dress as someone else to the same prom. But whatever, that's a different issue of embarrassment. Okay, so where do we stand? Want to make an announcement or so, two, before, and then maybe 3 announcements before sort of tackling administrative questions you have, and then maybe some subject matter questions you have before we dive in on some theory for the day, and then finally our lab. First thing I want to mention is that later today, I'm going to put online the homework that corresponds to what we've recently gone through and what we're doing today and next Tuesday or next Monday in class. Okay, so that'll be available later today. Some of the questions you should be able to handle already with no problem. Some of them are going to tie heavily to what we've just done, okay, what we're doing today, and some of them will even be related to material that will be corresponding to next Tuesday. Those homework questions will be due shortly following the exam. That's sort of poor timing. But hey, if you work on the homework questions to prep for the exam and then take the exam by Friday of next week when it's due, the benefit is you'll have the whole weekend without any homework to do, at least for this class. Okay, so definitely work away on the homework questions here through, I guess, about a week or a week and a day from now, next Thursday, to get you ready for the exam. I intend the exam to be such that you could take it shortly after we do the material in class. Okay, so after next Wednesday's class, you should be able to take it immediately. If you want to wait 2 days to do it, that's absolutely fine. That's my intent, actually, is to build in a little bit of study or review time where you can work with others in the class, maybe in some of those groups that you keep getting assigned into for the labs. That will be helpful. So that's one. Number 2, where we're at in the material is we're starting today to dive in on autoregressive models, AR models, if you will. And next week, we're going to start in on moving average models, MA models. MA models are different from the moving average procedure, okay? But between these two separate methods of modeling irregularity in a stationary series, you have the ability to forecast with greater precision, which who doesn't want precision in your forecast error? You can also avoid biases in your forecasts if you can simply model or understand the autocorrelation structure in the irregular term thoroughly. Now, as George Cox says, all models are false, but some models are useful. Over here, just to the side, I'm going to make an aside comment, and that's this. If we're close enough, we'll do better. Do you really believe the linear regression model is appropriate, perfectly working in every situation we use it in? No. Is it good enough to get you a better answer? Yes. Can it be improved upon? Well, if you run the linear regression model, then look at the residuals and see some slight curvature, you could model a curved pattern. In that same sense, we're pitching to you a story here, which we know to be likely false, but the degree to which the false story we're telling you starting today for the next couple weeks, the degree to which it's close to the truth in terms of describing the autocorrelation structure in the series is the degree to which it's useful. Okay. And then after that second exam, we're going to switch gears considerably into how to sort of deal with explanatory and response variables, both in a time series context. So today we're laying the foundation. We're going to continue doing that next week, early next week. And then after the foundation is laid, we're going to sort of dwell on these autoregressive and moving average models for a considerable amount of time. Okay, so one more announcement, and that is this. I sent an email to all the folks in the Tuesday, Thursday class, along with you all copied, so that way you know what's going on. The intention is from here on out, what we're going to be doing for that class session is I will be recording on Mondays and Wednesdays, like now, and I'm going to put online that video for those Tuesday, Thursday people to watch at their convenience. A couple of them indicated they had scheduling conflicts that would allow them greater flexibility if they could just watch it whenever they wanted to on Monday or Wednesday, or after we're done here, or perhaps even Tuesday morning. And then the Tuesday and Thursday class times, 9 till 10, I'll be there in the room, so to speak, but it's going to be more of a Q&A, assuming that y'all had watched the video. So if you do happen to, for some reason, miss on a Monday or on a Wednesday, the class session that normally you would attend, watch the videotape. That's fine. You could then pop in on Tuesday and Thursday between 9 and 10 to tackle asking me questions about, what, when the video said this, when you did that, what did you mean? Could you explain X, Y, or Z? That's easy to do. The Tuesday, Thursday class at about the hour break, 10 a.m., they'll be starting in on their lab, just like halfway through this class today, the 2-hour class, you'll be starting in on your lab. Okay? So I'm counting on you, the larger of the two classes, to ask questions in this class period about the theory, about the equations, about the notation. Anything we're doing, ask questions, because that will help them out as well. Okay, so that's one set of announcements. How about questions you might have on absolutely anything? And administrative questions first probably would be a good call. Matt.
Yeah, I just had a quick, I guess, kind of leading question. I was just wondering, it'd be super helpful to have at least solutions posted for all the labs and homework and stuff before the test.
Okay.
I was just wondering if you're...
Yeah, the homework solutions I will certainly have available. And on the labs, you're probably not getting a lot of feedback from the grader on the labs. But if you have something in mind, a particular lab question that you would like me to comment on, what is the right answer? just send me an email about that, and I will develop a set of, here are Steve's answers to these particular lab questions. Rather than fleshing out with every answer, focusing on the ones that aren't just cut and dry, the ones that most of you are like, okay, got it. So if there are things that you would like to talk about, I will make those lab answers available, but it's upon request.
Okay, makes sense.
Mhm.
So far, I was just checking, I don't have any grades, and I haven't talked to anyone who has any grades for any of the
Okay,
labs yet.
I'll check with the grader about that.
Okay.
I told the grader, hey, it would be great if you start grading the labs right away, but that doesn't mean that this grader has done it yet. So I got to talk to him. He's a stat major, so it makes it easier to hunt him down. And then certainly reminding him that because there's an exam coming up, focusing on the homework first, the first assignment would be really good. That's going to be what I'll tell him to make sure he does first. The labs is more of a, if you turned it in, you get nearly full credit. The labs are the learning opportunity. And if you still want to talk about something in a lab, like last time we had a lab, if you want to, no, not last time, but a week ago we had a lab. If you want to ask me any questions about those things in class is absolutely fine for that. Or offline, and we could make those answers available. So yeah, good. Matt lowered his hand. Anyone else? Okay, so how about subject matter questions? Did any of you have questions related to material that we talked about last time that you'd like to go over or discuss before moving forward into newer material? So I was talking to a friend of mine the other day, and he said, yeah, it must suck to teach advanced sort of math-based classes where in a regular classroom you can see students and you can see whether their eyes are glazing over and they're not understanding perhaps or bored versus if they're sort of following and nodding and then saying, yeah, that's, and, like you can see the smile on their face when what do you call that? Understanding happens. I'm staring at a list of names right in front of me, like Owen and Jenny and Sarah and Ethan and, et cetera. I'm not saying you should turn your video on, but I am saying that if you do have a question, you got to freaking ask, because I'm not going to have a clue. Whereas in a normal classroom, I would have a sense for whether I need to reemphasize something. So we got at least a video turned on. You got a question?
No.
Okay.
I'd say hi.
Hello. Okay, no, but yeah, so if I can, I'm not saying you should put the video on, but I'm saying there's more of a burden on you to ask questions as a class if y'all don't have the video on. If you do have the video on, I glance over and I see whether there's a sense of got it or that sort of a face, which means, okay, rephrase, Steve. Okay. So what I'd like to do, unless one of you wants now to interrupt real quick with a question. Is move forward into newish material. And I'm going to say, I'm going to assume from here on out, unless stated otherwise, that we're dealing with either time series that are already stationary, or which by a difference, maybe a first difference, or by a seasonal difference, will become stationary. So quick reminder, stationary. Constant mean, number one. Number two, the amount of variability doesn't change as time changes. Number three, the autocorrelation structure is constant across the different time periods. If you will, the ACF of the first 50 data points of let's share with you. I've got the S&P 500 data example from class last time, except for now we got 2 more days worth of data. the S&P 500 data here, the first 50 values, the ACF of those, and the second 50 values, the ACF of those two ACFs are really close, if not identical. Okay, so the autocorrelation structure, the autocorrelation function must be unchanging as we stretch across the different time periods. Not just the first, the most recent 50, the previous 50, but the 50 before that and the 50 before that, and yet again the 50 before that. That's the assumption of stationarity, okay? It's not impossible to check, but certainly it's hard to check whether the ACF is changing in its nature unless you do chunk out the data into the earlier, the middling, and the later bits and look at it. But theoretically, I'm going to, for now, assume that we have stationarity. Okay? So in the context of stationarity, if I were to read these data in, I might want to know, what does the ACF look like? So there we go, upstairs, the autocorrelation function. It looks like slow decay. I've called that previously a trend. Okay. I would also say, if it was not a trend, it could correspond to an autoregressive model. So we have to dive in and talk about what autoregressive models are like. This partial autocorrelation function, which we have yet to define, but we will define today, also screams out at me, autoregressive model. Literally, if I see something like this in the autocorrelation function and that in the partial autocorrelation function, I immediately think that could be an autoregressive model. Okay, so let's figure out what exactly that would mean. I'm going to share a whiteboard with y'all. Yes, go ahead. You should be, I think, can y'all see the whiteboard in front of you?
I have a question.
Oh, sure, yeah, please, Jenny.
So the ACF of the S&P 500 data, like, it had a slow decay, which would mean it has a trend, right?
Yep.
So then but then you said it was stationary, or we should assume that it's stationary?
Yeah, I was hoping someone would catch me at that. Thank you. Let's rephrase just to make it clearer, we hope. If you have what looks like a trend in the data, you'll see a slow decay in the autocorrelation function. But a strictly autoregressive model, yeah, could have the same sort of characteristics. Strong autoregression is about the same thing as a trend.
Okay, thank you.
So yeah, it's a matter of how you want to view things. Both are appropriate tools or techniques. You know, we could say, aha, I'll take the trend out and I'll look at what's left. But if I were to just assume stationarity in the S&P 500 values, I could still say stationary, but autoregressive. So let's first off remind you of what the autocorrelation function is. And so what the ACF of the sample it's literally R at lag K is equal to 1/nth of the total number of data points, YT minus Y bar times YT minus K minus Y bar, and that is T is 1 up to N. Okay, so if you're a little fussy, and math majors often are, and that's good, but you're sort of saying, well, hold on. We can't go back 5 time periods from the first one. What we're just saying is, for the available data, find this calculation. Okay, this is the autocorrelation function value. And if we had a mean of 0, the Y bar is 0. And later, in the more theoretical portion of today's discussion, we will say, let's suppose it was a 0 mean. Okay? But for now, I'm just going to say that is the autocorrelation. What about the sample-based partial autocorrelation function? I'm going to call that phi hat K. At lag k, the sample-based partial autocorrelation is found the following way. Regress yt on all of the previous k lags. Okay, so literally yt is beta 0 plus beta 1 hat times yt minus 1 plus beta 2 hat times yt minus 2 plus all the way up to beta k hat yt minus k. So if I were to do that, the beta k hat term is equal to phi hat k. Let's rephrase that. Controlling for all the intermediary terms already in the model, is there any benefit of including the next term, the kth term, in our model? So we already have a regression with a whole bunch of lags already. Is adding in this new term helpful? So it's something that you could calculate via regression if you wanted to. I'm going to say, well, the software will do it for us. What we're saying here is at a lag of 1, the previous intermediary lags, there aren't any. The slope, at a lag of 1 is noticeable. I could use y yesterday to predict y today. The S&P 500 value yesterday could be used to predict the S&P 500 value today. Well, that's what a trend would suggest. But this second partial autocorrelation function says, if I use yesterday and the day before that to predict the S&P 500 values today, the day before yesterday doesn't help me worth anything. Just yesterday matters. Or at a lag of 3, maybe at a lag of 3, maybe let's just sketch out what the PACF looks like for the S&P 500 data. I'm just realizing you all weren't looking at the screen I'm looking at. You're looking at the notes that I'm giving you. At a lag of 1, 2, 3, 4, 5, we see a spike at a lag of 1 right there. And at a lag of 2, it's like barely there. At a lag of 3, barely there, barely there, barely there. And that sort of zone of zeroness, we're not really outside that zone of zeroness for anything other than that first leg. So now with that partial autocorrelation function that matches the S&P 500 data, the one that I just sketched out for you, I'd say at a lag of 1, yes, I can predict successfully. I could predict tomorrow's S&P 500 value from today. And if I were trying to predict the S&P 500 value tomorrow from today's value and yesterday's value doesn't help me. Neither does the day before that or the day before that or the day before that. None of the other lags seem to matter. Any question about the partial autocorrelation function other than, yes, it's something that can be determined by regression? In the lab today and in the next discussion, we're going to talk about exactly how it works in a way that will help you read them. Here's the definition. We're going to have to sort of move forward to get you to read it. But questions now are fine. Okay, so let's go forward a little bit. And I'm going to define what I call an autoregressive model of the first order. So AR for autoregressive model 1 of the first order. Okay, and I'm assuming that the expected value of YT is 0 for this particular discussion. As we already mentioned, if I simply take away from the original series the average, if I remove the average from my original series, that's going to be satisfying this condition. And rather than dealing with the extra complexity of 2 or 3 extra terms in every equation, I'm just going to say, suppose we have a centered series with a mean of 0. It cuts through the work that we do on the paper. So I think that's helpful. If that's the case, yt is phi times yt minus 1 plus epsilon t, where the epsilon t's are white noise. And I'm going to say normal white noise with mean 0 and variance sigma squared epsilon. Let's rephrase that just a little bit. The epsilons being white noise and normal, the white noise means independent of each other. Every single epsilon is completely unpredictable by any of the other epsilons. Independence, that's all it means. And the fact that it's normal and has a constant variance that is necessary for ultimately our series or our process to be stationary. Okay, so if this is the case, you're sort of thinking, aha, maybe that looks like a regression model. That looks a lot like a regression model. Yeah, literally, I can say, shoot, I can say that's a regression. So if I were to fit the model yt equals beta 1 hat times yt minus 1, okay, you're going to say phi 1 hat, the PACF value, is equal to approximately phi. Okay, so the PACF at lag 1 is about equal to phi. If I were to fit a model, yt being a beta 1 hat times yt minus 1 plus beta 2 hat times yt minus 2, if I were to fit that model, but the truth is only that the previous value y matters, okay, I'm going to say, well, here's the truth in green. Compare it to our model. This beta 2 hat should be approximately 0. So the PACF at lag 2 should be about 0. And if I tried to fit a model with 3 lagged y's, you'd see the partial autocorrelation function. Again, doesn't matter. Our model itself, the AR1 model, says only the one previous value, y lagged 1 time period ago, that's the only thing that matters. Any question about that? Okay. So what I want to do now is dive in and talk about the theoretical autocorrelation function. Okay, so that's the sample-based partial autocorrelation function. We talked about what it should look like. What about the theoretical ACF? So for the AR1 model, again, yt is phi times yt minus 1 plus epsilon t. The theoretical ACF, theoretical autocorrelation function. Let's approach that via the autocovariance function, okay? Again, gamma at lag k, the autocovariance, is equal to the expected value of yt, and because we have a 0 mean, I don't have to worry about subtracting out the mean of yt, times yt minus k. So the expected value of that product right there. So gamma 0 is the expected value of yt squared. We could call that also the variance of yt, or sigma squared of the y's. Now, just as a quick note, sigma squared of the y's, the variability in the y values is different than sigma squared of the epsilons, but they're related. We will see in a later lecture how exactly you could determine the relationship between sigma squared for the epsilons and then sigma squared for the y. But for now, I'm just saying the autocovariance at a lag of 0, or the variance over the series, or the expected value of yt squared, that's a constant sigma squared y. How do I get after gamma 1? Gamma 1, the autocovariance at a lag of 1, is by definition the expected value of yt times yt minus 1. Now I'm going to sub in for yt what it equals. Circled upstairs in blue. So that's the expected value of now phi yt minus 1 plus epsilon t times yt minus 1. And doing algebra. And if, okay, so here's the deal. Different people have different algebra backgrounds. Most of y'all are pretty good at it, but I know as a fact, I have sometimes been in a classroom and asked the question, hey, where did that happen? Or how did this work? And I was really glad I asked, even though a couple people giggled. The reason was I didn't immediately see the thing. And when I was reminded, I'd say, oh yeah, that. There's no shame in asking for a question. In fact, it's a bad idea to not ask a question. So any questions? Yes. Okay. So using algebra, the expected value, we're going to find that this is phi times the expected value of yt minus 1 squared. Plus then the expected value of epsilon t times yt minus 1. But I know that that's equal to sigma squared y, or it's equal to gamma 0. The reason is that gamma term, the variance of the series, doesn't depend on where you are inside the series. If I ask you, what is the variance of the series? You'd say, oh, 12. You give me a number. If I say, now go back a day from where you were standing, what's the variance of the whole series? You'd say, it's still 12. The spread is still 12 vertically. The variance being unchanging across the different time viewpoints says that whether it's the expected value of yt squared or the expected value of yt minus 1 squared, it's the same thing. It is just gamma 0. And because this epsilon is independent of everything that's happened in the past, that whole term zeroes out entirely. That's all 0. So we would say, yeah, gamma 1 is phi times gamma 0. That's easy. Any questions about the algebra here? Yeah, literally in these lines here, there may be some things that, depending on your background, you might not have seen before. Rules of expectation and variance. Matt, you got a question?
Yeah, this isn't. This is more conceptual than about the algebra. But
Sure.
Could you just say what that final expression is like in words without symbols? So like the gamma 1 is. I guess I'm getting like a little bit lost. I know the phi is the partial autoregression function.
Yep.
But then what's the gamma again?
Gamma is the autocovariance, but we don't speak variance or covariance naturally. Let's convert a covariance into a correlation, then we'll answer your question. How about that, Matt?
Okay, perfect.
Okay. So to get rho a theoretical, can y'all read the yellow? Okay. And let's just, actually, let's go with black. Rho at lag k, the autocorrelation at a lag of k, in theory, is equal to gamma k over gamma 0. In this case, then, rho 1 equals gamma 1 over gamma 0, which is just phi times gamma 0 over gamma 0. That's just phi. The autocorrelation at a lag of 1 is just phi. In my initial setup, phi matters. Phi describes the autocorrelation. Okay, so did that help, Matt?
I think so. So could you just say exactly what you said one more time? I just need like a second more to process it.
Yeah, the autocorrelation function of the AR1 model at a lag of 1, the ACF, the autocorrelation function, is just phi.
Okay, yeah, I think that makes sense.
Yesterday's value times phi is today's value. Once we add an error, the times thing, the phi that we multiply yesterday's value by, is also equal to the autocorrelation function at a lag of 1. Hey, what about a lag of 2? Gamma 2, by definition, is the expected value of yt times yt minus 2. And I'm going to sub in for yt what it is. That's equal to, yt, no. Erase. There we go. It's phi times yt minus 1, plus then epsilon t times yt minus 2. Now here I can, again, do algebra. This is going to be phi times the expected value of yt minus 1 times yt. Okay, again, the yt minus 2, I apologize, yt minus 2 here. Yt minus 2 times yt minus 1 times phi. We need the expected value of that. Plus then, we've got the expected value of epsilon times yt minus 2. Epsilon t, yt minus 2. Okay, so let's see what those things are. Like before, a current epsilon in expectation cancels out anything in the past. The expected value of something that's random and means 0 times something from the past is definitely gonna be 0. What about the expected value of yt minus 1 times yt minus 2? On the previous slide, we learned to call that gamma 1. That's gamma 1. So let's go back and verify that that's gamma 1. I'm going to sort of switch to the previous slide. Yeah. The expected value of yt times yt minus 1 is gamma 1. And we also said the autocovariance doesn't depend on what time period you're standing at. If you're standing at now and saying compared to yesterday, or if you're standing at yesterday and comparing to the previous day, it's still the same autocorrelation structure. So gamma 2 here is just phi times gamma 1. But we know gamma 1 is just phi times sigma squared epsilon. Actually, let's change gears a little bit. Let's go with rho 2. Rho 2 is the autocorrelation. We speak autocorrelations. Let's go right there real quick. The autocorrelation at a lag of 2 is going to be gamma 2 over gamma 0, which is just phi times gamma 1 over gamma 0. But gamma 1 over gamma 0 is just, we found phi. So this is phi squared. Okay. The approach that we're taking here, I think is actually rather slick, and I'm going to sort of tell you exactly how you could deal with this autoregressive model of the first order. Then we'll talk about autoregressive models of the second order, and we'll leave the third order for the lab. You'll do the first and the second order also, but then you'll eventually end up at the third order. The approach that we're talking about is eventually, once you flesh it out, called the Ewell-Walker equation. And the Ewell-Walker equation for an AR1 model says that rho k, for the AR1 model, says rho k is phi times rho k minus 1. And as long as you know rho 0 is 1 and rho negative k equals rho k, I mean, shoot, is the correlation of height and weight equal to the correlation of weight and height? Yeah. So it doesn't matter which term you put first. If you're standing and looking forward a day, it's the same correlation as if you say, well, let's stand and look back a day. A one-day shift is all that matters here. Okay? So the Ewell-Walker equation says that eventually the ACF in theory is the following. Rho k equals just phi to the power k. There you go. That's it. So you can see why this is going to look like geometric decay in the autocorrelation function. If I had phi being 0.9, the first term is 0.9, the second term is 0.81, the third term is 0.72, the fourth term is 0.63 or so. And it's going to go down by multiplying by 0.9 every single time. Almost a linear decay. It literally is geometric, but in the short range up at the beginning, it looks sort of linear. What about the AR2 model? Well, we depend on the previous two terms. Yt equals phi1, yt minus 1, plus phi2, yt minus 2, plus epsilon t. That's the AR2 model. And so you can imagine the PACF is going to have the following shape to it. At a lag of 1, we're going to have a spike. At a lag of 2, we'll have a spike, and then zeros from there on out. Because if I were to take y and regress it on not just the previous 2, but maybe the previous 3 or 4 or 5 terms, the third, fourth, and fifth lagged y values would be uncorrelated with zero slope related to the current y. In the PACF, you see 2 spikes if it's an AR2 model. 1 spike if it's an AR1 model. My guess is 3 spikes if it's an AR3, 4 spikes if it's an AR4. You'll verify that in the lab today. What about the theoretical model? Now I'm happy to, I'm happy to, if you'd like, derive for you the Ewell-Walker equation for the AR2 model. I would rather at this stage just tell you what it is and show you how to use it for the AR2. We'll later, if y'all ask, talk about deriving the Ewell-Walker equation. The AR2 case looks the following way. Rho k equals phi1 rho k minus 1 plus phi2 times rho k minus 2. And as long as rho 0 is 1 and rho negative k equals rho k, we are good to go. Okay, so I sort of think I could now, with this AR2 model, tell you about the theoretical autocorrelation function. Okay, let's go ahead and work in green. I'm going to say rho 1 is phi1 times rho 0 plus phi2 times row -1. But I know row 0 is 1, so that's just phi 1. And I know row of -1 is row of 1. So I've got a row 1 on both the right and the left-hand sides. Let's do algebra. Row 1 minus phi 2, row 1 equals phi 1. Or I guess I could write that as row 1 times 1 minus phi 2 is row 1. I'm sorry, row 1 times 1 minus phi 2 is phi 1. So row 1 is phi 1 over 1 minus phi 2. So if I tell you the value of phi 1 and phi 2, you could tell me the autocorrelation in theory at a lag of 1. Or 2 or 3 or 4. Actually, that's sort of a nice feature in this Yule-Walker equation. We could, for a lag of 2, redo it. Row 2 now is phi 1 times row 1 plus phi 2 times row 0. Well, I know those terms. That's just phi 1 times row 1. That's phi 1 over 1 minus phi 2 plus phi 2. Well, row 0, that's just 1. So I write that as phi 1 squared over 1 minus phi 2 plus phi 2. The ACF at a lag of 2, completely calculatable by the values phi 1 and phi 2. I could continue. Let's go ahead and save this and then add one more line. What about row 3? Row 3 is phi 2 times row 2 plus phi 1 times row 2 plus phi 2 times row 1. Now that's just phi 1 times what we earlier had, phi 1 squared over 1 minus phi 2, plus then phi 2, plus then row 2 times, or phi 2 times row 1, and row 1 is phi 1 squared over 1 minus phi 2. And I'm thinking that's sort of a bit of a mess, but I think two things. One is I like the way that looks because it reminds me that's just phi 1 times row 1 plus phi 2 times row phi 1 times row 2 plus phi 2 times row 1. If you wanted to do a little bit of additional algebra, you could probably re-express it in a more concise way that math types like, and that's fine. I'm saying to myself, though, could you plug in a phi 1 and a phi 2 and tell me the number? Yeah. Shoot, row 3 or row 4 is just going to be phi 1 row 3 plus phi 2 row 2. Again, repeat the process on and on and on and on. And what I'm spotting is ultimately over time, we end up with lots of squares and cubes of numbers that are in the range negative to positive 1. We end up with smaller and smaller values in the ACF for our AR2 model. Let me leave you with how to do this with the Yule-Walker for AR3, or better yet, the ARK case. ARP. If P is the order of the autoregressive model, the ARP model says row K equals phi 1 times row K minus 1 plus phi 2 times row K minus 2 plus all the way up to, finally, phi P row K minus P. Then, as long as I remember row 0 is 1 and row 1, or K, negative K, equals row K, I can then solve for any of the autocorrelation function values at any theoretical lag. Okay. So I think that's a lot
Question.
to glom on. Oh, please, question.
What do you mean by row negative K equals row K?
Do you want me to explain it conceptually or algebraically?
Conceptually.
Conceptually, if I'm standing here and looking back in time, me correlated with, you know, what happened a day ago is the same thing as standing here and looking forward a day in time. If I look backwards across the S&P 500 values, 1, 2, 3, 4, and 5 legs, it's the same thing as looking forward 1, 2, 3, 4, and 5 legs. It's the same autocorrelation structure going backwards or forwards.
Okay, that makes sense. Thank you.
Or,
So is that,
oh, can I just draw one more thing?
Yeah.
Yeah. The ACF itself has a lag at 0, height of 1. And we're really saying it sort of decays slowly on both sides, both ways. We just only tend to present the positive part. Okay, so.
so is that a condition that has to be met, or is that just like a fact that we're stating?
This guy here?
Yeah.
Yeah, it's a condition of stationarity.
Okay, gotcha.
Yeah, so if you have a trend in the data upwards, if you have the series changing its variance as time changes, if the autocorrelation structure changes as time changes, you can't do this.
Okay,
Non-stationary series, it's a whole different ball of wax. Okay. So what I want to do is to sort of close things out. If you have any questions right now on any of the material we've talked about, now's a great time to talk about it with me. Otherwise, you're going to be going into the lab where you'll be following through and generating some. Oh, no, I'll show you one more thing first. And then we'll go into the lab. I'll just show you 2 separate ways of generating autoregressive models. And you'll see that it's working out pretty nicely, okay? So if I wanted to generate an AR1 model, I could construct a collection of epsilons, maybe 1,000 of them. And I could literally say, what if my phi value was 0.9? Shoot, undo. There we go, undo. It's the typical Windows Mac thing. Okay, so Control Enter. There we go. Ran that. And then if I were reading the code, basically it says the next y is that phi 0.9 times the previous y plus an uncorrelated epsilon. Okay, so I'm just going to generate these values, these y's, and create this thing called a YT. If I look at the ACF of YT, it's right there. It's that same sort of decay that we talked about. 0.9, 0.81, 0.72, 0.63, et cetera, et cetera, et cetera. As we're drifting down, you see them getting lower and lower. Another approach besides the do it by hand with a for loop is to use the ARIMA sim command. I'm not telling you what you should do. I do think there's some benefit in actually you control everything. But if you like just using functions that are pre-built for you, the ARIMA sim function says, give me 1,000 things from a model where it's an AR model and there's a value phi1 in there. One phi, it's phi1. If I create that xt that way and show you the ACF of xt, it looks just like the ACF of yt. These are the same process. ARIMA sim, I like a little bit better, but I think there's something to be said for looking at the actual code. Just for an AR2 model, the notation for the ARIMA sim is the following. ARIMA sim, give me 1,000 things from a model where there's some AR terms, phi1 and phi2. I guess I should specify what phi1 and phi2 are, 0.7 negative and 0.2 positive. Now, if I say my model has those values, 0.7 and then negative 0.2 as my negative 0.7 and then 0.2. Let's look at the ACF and the partial autocorrelation function there. You could see in the ACF slow or geometric decay. It looks like it's alternating in sign. That doesn't trouble me at all. You'll see examples in the lab today of that. But also, like we claimed earlier, if there are two values phi1 and phi2 in the model, you'll see exactly 1, 2 spikes in the partial autocorrelation function. That's what we see here. 2 spikes in the partial autocorrelation function, then zeros, that says AR2. My guess is if you had 3 spikes, yeah, it would be AR3. But again, that's for y'all to tackle on the lab. Okay, so any other questions before I sort of turn you loose into your groups?
Yeah, one question.
Yeah, Eric.
Yeah, so how would you define the difference between the autocorrelation function and the partial autocorrelation function?
Well, the autocorrelation just looks at the correlation between now and 10 time periods ago. Mm-hmm. The partial autocorrelation says, if I control for all the intermediary lags, is there any correlation between now and 10 time periods ago? This ACF at lag of 10 says, I can predict from 10 time periods ago what today is going to be like. The partial autocorrelation says, if I have a lag of 1 and 2, and 3 and 4, 5, 6, 7, 8, and 9, and a lag of 10, I am not any better off. It's all in the first 2 lags where my predictive power lies. The partial autocorrelation tells you where you are benefiting from your predictions. And lags of 1 and 2, and that's it. Eric, does that answer your question?
Yeah, it does. Thank you.
Cool. Okay, so I'm going to sort of shift you into these groups. Hopefully the not random, but the pre-assigned groups will work out nicely. Breakout rooms. Let's see if you're all in a room somewhere. And, oh, yes. There is one of you who is in a room by themselves. I will quickly adjust that. Yes, and then put that. Oh, I'm going to have to then put that person in another room later. I apologize. So you're all but one of you going to a room, and then one of your groups will have someone join them rather shortly, and then work away in the lab. We're all good. Bye-bye.